Hello and welcome to my channel. As I promised you last time, today we're going to make a robot arm, mostly 3D printed, very cheap robot arm. Very cheap but capable robot arm. And for this I already prepared these actuators, which we have designed last time in my last video. And also I have prepared these parts, but I still need to 3D print some more parts, and some of the parts like this one I need to reprint. So there are a lot of work to do. And also I should say that I have not tested this actuator, so I don't know the maximum payload, but I'm quite confident in them, and so I think this robot arm should work. But as I never tested them, I don't know exactly. So this is going to be the main question of this video. Is this robot arm is going to work? And also I need to make the electronics for this robot arm, meaning the controller with the drivers. And for this I still don't have all the parts, but they're coming. So I hope by the end of this video this robot arm is going to work, but I'm not sure. We'll see this. So let's get started, there are a lot of work to do. This video is sponsored by GLC PCB, more about this later. So for this robot arm I'm going to use the TNZ and TMC5160, and this is a test bench where I can test different software for the TNZ in order to see how it works. On the robot arm I'm going to use the home switches, the simple ones, to make everything cheap. And also I'm going to use the thermostats. These thermostats, they are normally connected, so these two pins normally connected, but when the temperature of this thermostat goes higher than 50 degrees, it disconnects these two pins. So like this I'm going to monitor the temperature of the motors, and if the temperature of the motors is going too high for our PLA plastic, I'm going to stop robot arm. Thus we will have the thermal protection on this robot arm. I think this is a really cool idea and it's quite cheap. I have removed all the support material, and now let's start with the axis number 5. And afterwards we will go to the axis 4, 3, 2 and 1. The end effector is going to be connected over here using these 4 holes. And this piece goes on the axis number 5, just like this. This is the easiest part. As the next step, this actuator goes on this piece, like this. But before doing this, we need to install the home switch over here, and we also need to install the thermostat on our motor. The home switch goes over here, and it's going to be fixed with the zip tie, like this. Afterwards we fix it over here, but before I need to solder the contacts. So this switch is going here. So now we have this bump over here, and this bump is going to push our home switch. And for this bump I use a screw with 27mm length. And for this I took a longer screw and I cut it. To install the thermostat I'm going to use this 3D printed piece, where we can install the thermostat like this. And I'm going to use a thermal tape for the better thermal contact, which will go over here. And with the zip tie we're going to fix it to the side of the motor, something like this. The actuator for the axis number 5 is fixed, and now we have also the thermostat. Next, axis number 4. So over here I did a little bit of cable management, and I have installed the limiter for the axis number 4. Also I have connected axis number 4 to the driver, and let's see how it works. Yeah, it works quite nice. There is enough power at least to lift itself. And over here I will put the motor on the right. Like this it's going to be easier to assemble the next piece. Look at this cable mess. Actually it's not so complicated. As you can see, I have fixed axis number 3. I have connected this axis to our driver. Now let's see if this actuator with this driver would be able to move this piece. Basically like this we simulate the part of the robot arm, but without any payload. Cool, it works. In the same way, I have assembled two other axes. As you can see, the robot arm assembly is going quite well. I would say it's even better than I was expecting. And I've just received the package from GLC PCB. Basically, it should be PCBs for the controller of this robot arm. I use the GLC PCB mainly because they have a good service and they are really fast. So you can make quickly your PCB on the Easy EDA, and afterwards you can upload your files to the GLC PCB website, and after a couple of days you have your PCBs. I ordered a lot of them. So there are two types of PCBs. This one with the driver and this one with the Tinsy. And they should connect one to another. So you can connect multiple drivers to the single Tinsy module. So this is the Tinsy module. And this is a driver module. So on the single Tinsy module, it should be possible to stack multiple drivers. I think up to 8 drivers per one Tinsy module. These are schematics of the driver board and Tinsy board. These schematics and PCB layout are made in Easy EDA program. What is good about Easy EDA? It is a simple program to learn. It runs in your browser, no need to install anything, and it has extensive component library where you can find everything. Also, they have a pro version with extended capabilities tailored for professional users. It is super easy to order. Just go to glcpcb.com, click Order Now, upload Gerber file from Easy EDA. First I uploaded the Tinsy file, then the driver file. I've ordered 24 drivers boards and only 5 Tinsy boards. Like this I have 5 driver boards for each Tinsy board. The price is quite low, and after a couple of days I had my package at home. So let me solder everything and we will test them. I hope I have not made any mistake. I have soldered all the components. I'm pretty happy with the result. This is input-output connectors, which you can use, for example, for the limit switches. Over here there is 3 pins for the serial port. These 2 pins in order to select the power from the USB or the power from the board. By the way, the main power is 24 volts. Over here, this connector goes to the motor. These are connector for the potential encoder, but I'm not going to use it over here. It's just in case. And over here, we select the board number. So if you have multiple boards stack, you need to put, for example, this is the ID1, ID2, etc., etc. You can stack up to 8 boards together. There is one small problem that power converters, they're a little bit too high, and so you cannot stack the boards like this. This one, the Tinsy board, should be on top, but this is not a big problem. Here I put the standoffs, 10mm standoffs. Let's try to stack them at the first time. Oh, this is quite cool. Hehe. There is a gap here for the washer. It looks really cool, but I hope that it works too. I have put the appropriate program to the Tinsy. This is a simple program which should only run the motor in one direction one turn and in opposite direction one turn. The motor of the axis number 1 is connected, and I also have connected this power supply with emergency stop button. So first of all, the power supply. There is a blue LED over there on the driver board. So the power is connected. Now I need to connect the USB to give the power to the Tinsy. And look, it works. It's kind of hard to see because the reduction ratio is high, so the motion, so one turn of the motor is just a fraction of the turn of the actuator. But it works. So great, it worked from the first time. This means that I have not made a major error on this board. I have soldered all the boards, Tinsy one, and 5 boards with the drivers. And also here with the jumper I put the ID for each actuator. And here all the boards stuck together. Tinsy and 5 boards with the drivers, with the TMC 5160 drivers. And in my opinion it looks quite impressive. At the same time it's quite compact. For the 5 motors driver, it's really compact. And I should say that these drivers are quite powerful. They can drive NEMA 23 motors. It would be nice at some point to make a 3D printed box for it. The mechanical part of the robot arm is mainly finished with all the limiters. At the base there are all the cables. There are 5 cables from the motors and 1 cable from the home switches and thermostats. All the home switches and thermostats, they are connected in series. I know that you're going to hate this, and I know that you're going to put this in the comment, but for the moment it's like this. I think it should be good enough. Like this I cannot say which home switch was pushed, but at least I can say when it was pushed. I have mounted all the drivers and Tinzi on this plate, and the idea is that this plate will go over here like this. So all the drivers are going to be installed inside the base. This is perfect. I'm really happy with this electronics. I think I'm going to use it in my future projects a lot. It's nice that I ordered many of them. This part is just press fit inside, no need for any screws. And anyway, when we will fix this robot arm to the base, to the stationary base, this plate is not going anywhere. We have only 2 cables coming out, USB and power. I have made this frame. This is definitely overkill, because here I use 2040 profile for these 3 and 4040 profile for these 2. And all of them have the length 50 centimeters. Okay, I hope that I'm not going to make fall this robot arm. This would be disaster. And the robot arm is fixed. I thought that it's going to be smaller. It looks not really small actually. And this is me compared to this robot arm. Cool, put the like for this. This is definitely extremely beautiful robot arm. Perfect robot arm for DIY community. And now it's the best moment to check the backlash. So the overall backlash is over here, quite high. It's around 1 centimeter. Now let's see the backlash of individual actuators. So this is the backlash of the smallest actuator. The backlash of this one. And for the biggest actuator. So as you can see, it's not 0 backlash actuators, but I never thought that it's going to be 0 backlash. But still, this backlash is not huge. It's quite big, but for the 3D printed actuator, I think it's really good. Of course, you can make smaller backlash with 3D printing, but in this case, it will wear quite quickly, and you will still have a quite high backlash after some time of usage. With the 3D printed actuators, there are kind of a trade-off between backlash and efficiency. When you have some backlash, you have quite high efficiency, but when you lower the backlash by increasing the size of the gears, in this case you will increase the friction inside, and like this you will decrease the efficiency. And now the calibration sequence. I have speeded up this video because the calibration is slow in order to be precise and safe. Brought so much joy, couldn't wait for the presents and laughter. I couldn't sleep late at night, looking for Santa with lights. Those are the memories I still remember. Then I became a man, lost sight of who I am, but right in front of me was the answer. 'Cause on Christmas I feel joy, and I turn back to a boy. And the calibration is done. And the robot is in home position. So every joint in its middle position. Cool, it works. Yay! There are some oscillations, but I think it could be managed in the software. And so this is the calibration sequence. Each actuator moves first in one direction and it goes up to the limit switch. And afterwards it rotates to another direction, also to the limit switch. And like this it knows the limit on the right, the limit on the left, and it's going to put itself in the middle. Now the same for this axis. So first of all, this part of the limiter is going to trigger the switch, and afterwards when it's going to move to another direction, this part of the limiter is going to trigger the switch. The motor is not very hot. Actually, it's not hot at all. Now also let's see if it's going to resist. It's quite good. It's quite good. This motor is quite weak, so it needs to be changed. Let's see if it can handle. Yeah, you hear? This is a skipping steps. Now the calibration of this axis. And on this axis we don't see much oscillations. Let's also push it to see if it's going to skip the steps. It's quite good. It's quite good. So all the problems in elbow right now. Let's try again to push it. Yeah, it's quite good. It's quite powerful. Cool, I like it. So we just need to solve the issue with the elbow. And I think if we will change the motor, it will solve all our issues here. All the files are going to be available on my Patreon page. So let's check the temperature of the motors. This one is 30 degrees, no problem. This one is almost 30 degrees, no problem. And this one in the elbow, it's around 35 degrees. Yeah, this is the weakest point of this entire robot arm. That's why I do plan to change this motor to this one. This is 34mm long motor and this one 39mm long motor. So this is more powerful. It's actually like 25% more powerful than this one, and at the same time it works at 1.68 amps and this one works at 0.4 amps. So this one is more suitable for my drivers. Don't forget to subscribe to my channel and put the like to this video. I think this video is already quite long and it's difficult for me to edit the long videos, so I would like to stop here. And for the next time we're going to change the motor in the elbow. We're going to put more powerful motor and the motor which is more suitable for our drivers. And also I would like to finish the software for this robot arm. Like this we can control it with the Raspberry Pi using the Python, and like this I would be able to run this robot arm with the PS4 joystick. This would be fun and it would be also easy for testing. And also in one of my next video I'm going to do the test of each joint to see how much payload they can handle, how fast they're going to wear and how fast we can move them. I think you're all waiting for this video. It's coming. As usual, huge thank you to people who support me via Patreon and via YouTube channel membership. Here's their names. Thank you guys and girls, you are the best. Stay safe, good luck with your projects and see you next time.